Hi everyone, and welcome to another seminar of Physics Latam. Today we are very happy to have Professor Jethro van Ekeren with a talk on notions of vertex algebra. Jethro is an assistant professor of mathematics at IMPA in Brazil. He completed his PhD in mathematics at MIT under the supervision of Professor Victor Kat. From 2015 to 2023, he was an assistant professor at the University Federal Fluminense. His research interests are in algebra and representation theory, with particular focus on algebraic structures arising in theoretical physics, such as infinite dimensional algebras, vertex algebras, and chiral algebras. Remember to raise your hand at any point during the talk if you have any question, and now I'll leave you with Jethro. Please go ahead.
Okay, great. Thanks so much for the introduction and for the invitation. So I'm going to, because I'm using this laptop as a tablet, I'll have to switch off the video in a moment. Let me just first say I had a quick look at the notes from the course that's going on infinite dimensional algebras, and I think what I'm going to say today should fit in quite well with what was in, I believe, lectures 2 and 4 of the course, where you saw the oscillator algebra, or the Heisenberg Lie algebra, its Fock-space representation, and the construction of a representation of the Virasoro Lie algebra in that. So I'll briefly review that material, and going from there, we'll sort of see the notion of vertex algebra naturally arise. Okay, so okay, so I hope you can see my screen, and I hope you can hear me.
Yes, I can hear you and I can see the screen.
Okay, great, thanks. So we have this vector space, which we call Fock space. In the simplest case, it's given by polynomials in infinitely many variables, like that. This carries a representation of the, what I'll call oscillator Lie algebra. Which is Laurent polynomials plus a central term. Here, actually, maybe I'll write HM instead of T to the M. Okay, and the representation was given by Hn goes to, it will depend whether n is positive or negative. So it'll be multiplication by minus n if n was negative. It'll be partial derivative if n is positive. And we can set 0 if n is 0. Okay, so this defines a representation of this Lie algebra in the vector space H. And we can actually vary this construction a little bit. define H, I'll call it H mu. This is H as a vector space. With H0 being mu times the identity. So here mu is some complex number. If n is different than 0, we define the operators in the same way as before. The only thing that we change is H0. Okay. And this idea appeared to define some operators, Lm, given by 1/2 sum, where k runs over the integers of hk, hm minus k. And now if m, so these are endomorphisms, of h, what's happening? Sorry, I don't know what's happening to the screen. Now, this is well defined if m is different than 0. And the reason for that is basically that hk and hm minus k in that case will commute with each other. And there's a key observation, which is that if for each vector v in H, hkv equals 0, we'll say there exists n such that hkv equals 0 for all k greater than or equal to n, okay? And this is easy to see because without loss of generality, you could take v to be a monomial. Now, among all the x's that appear in that monomial, one of them has a greatest possible subscript, let's say x sub 100. Then if we look at the action of hn on such a monomial, as n becomes larger and larger, we're taking the partial derivative with respect to x sub n. As soon as n is bigger than, say, 100, then this partial derivative starts to annihilate this vector. Okay, and this happens for every vector in H. Okay. But still there's a problem with L0 because the operators hk and hm minus k don't commute. So what one does is define Lm to be 1/2 sum of the normally ordered product, hk, hm minus k, nz, where now this so-called normally ordered product, by definition, is if, let's say, if n is negative, no, I'm sorry, if n is greater than or equal to 0, then we leave the terms in the order they were. But if n is negative, then we swap the two. So I'm just going to take a moment to clean the screen of the tablet to see if that helps. Okay, so now all of these operators, LM are well defined. An explicit computation, which is quite a complicated computation, shows that the Lie bracket, these operators, satisfies the relations of the Virasoro Lie algebra. Where I'm going to write C times the identity here. There's a representation at C central charge equals 1. The idea of vertex algebras is sort of a language to organize this sort of computation. And the other key idea of vertex algebras is that we work with generating functions instead of individual operators. So what do I mean by that in this case? Let's define, let's consider h n, z to the minus n minus 1, n runs over the integers. This is a generating function, which I'll call hz. So all I've done is gather all of these operators hn into a generating function. The choice of power z to the minus n minus 1 at the moment you should think of as purely a convention. I could have chosen any convention I wanted. Okay. Now, we know that hm and hn have this commutation relation. So actually earlier on I should have mentioned also that the central term k was sent to the identity operator on h. So now let's see what happens if we re-express this relation in terms of the generating function h of z. There's now some hn. M delta. So really this reduces to a sum on one of these variables. So I'll write this as on M, like that, okay? So what kind of power series do we have here? Well, if this power series, so the sum runs over all the integers. So let's remark, if I had considered, it looks a bit like a geometric series though, if it were a sum over positive integers. So let me explain that. So if we took the power series expansion of 1 over z minus w, would get something that looks more or less like half of this sum, right? And similarly, well, actually, how to get exactly this sum? So we see that here we've got z to the minus m minus 1, that's right. But instead of w to the m, we got m times w to the m minus 1. So actually, we should take the derivative with respect to w of this series. So w. Okay. So actually, I might put a little symbol here, I zw, to indicate that here I was expanding in positive powers of w. So similarly, if we expanded in positive powers of z, so then we'd get minus some m negative of m z to the minus m minus 1, w to the m minus 1. Okay. So actually, what we have obtained as the commutator of our field hz with hw is the difference of these two expansions. They're actually two expansions of the same function. Oh, sorry, I should say, again, dw here. So dw of, let's say, izw minus iwz over z minus w. Which is to say iz z minus w squared. Okay. So now this kind of difference of two expansions of the same power series in two different domains, I'm going to write this, well, I'm going to invent a notation. The notation will be delta. This should suggest the Dirac delta function. In a moment, I'll explain why. So notation will be delta ZW is IZW minus IWZ to Z minus W. Which concretely is just the sum of all integers of Z to the minus M minus 1. That leaves the M. Okay. What's happening? Yeah, so why would you identify such an object with the delta function? Well, by way of motivation, I'll just mention an identity of distributions from classical analysis. It's the delta function equals 1 over, there's a 1 over 2 pi I normalization factor. And the idea is if we take the function x minus I epsilon, 1 over x minus I epsilon. So this is a function which is regular for all real values of x. It has a pole, but it's in the complex plane. We could similarly take x plus I epsilon, and then their difference is also something that's regular on the real line. As we take the limit as epsilon goes to 0, then this function becomes more and more singular, and it basically converges to the Dirac delta distribution. Okay, so this difference you see of two expansions of this function 1 over x plus or minus some parameter epsilon should sort of remind you of this difference between two expansions IZW and IWZ, the function 1 over z minus w. Okay, so that's all I'll say about that. You could also think of this definition that I've written just as a purely formal definition. Okay, so I apologize that my tablet is not behaving very well here. So in summary, we have h of z, hw was the w derivative of our delta function. And just a little remark, the delta function has this property that if you multiply it by z minus w, you get 0, which is kind of reminiscent of the property of the actual, of the delta distribution, right? That x times delta of x is equal to 0. Similarly, if you take the derivative, actually, let me write it this way. Let me take n derivatives of the delta function. Then if I multiply that by z minus w to the k, then this will be 0 if k is greater than n, and it will be n minus k derivatives, the delta function, if k is less than or equal to n, okay? And here when I write n with brackets, I mean 1 over n factorial. derivative n times, okay? So I'm just writing that identity because it'll be convenient later on. And it would be a good exercise to prove it. So in particular, since the commutator of h of z with h of w gave the derivative of the delta function, we know that if we multiply the commutator by z minus w squared, we'll get 0. Okay. Now, this kind of identity, where we take some generating fields, some generating functions like hz. So these are going to be called fields or quantum fields in the theory of vertex algebras. And if when we take the commutator of two of them, we get something that's annihilated by some power of z minus w, we give a name to this property. We say that these power series or fields are local. Okay, so let me start giving some definitions and propositions. Actually, before that, let me say, let V be a vertex algebra, a vector space. And A of Z be a formal power series where these coefficients an are endomorphisms of V. So we say A of Z is a quantum field on V if for every vector in V, there exists n such that A sub nv equals 0 for all n greater than or equal to n. Okay. So an example is h of z acting on H, a Fock space. Right? Precisely because of these comments that I made earlier about if you differentiate with respect to x to the n, then for n sufficiently large, this is going to give 0 when applied to any particular vector. Okay, so we have an example of a quantum field already. Next definition. We say two quantum fields A of z and B of z on V are local or form a local pair if there exists n such that when we take the commutator of A of z and B now of W, then multiplied by some sufficiently, there exists n such that this gives us 0, okay? So our example is that hz is a local pair. Okay, and the importance of this notion of local pair is that it implies or is equivalent to the fact that the commutator of the quantum fields will always have an expansion essentially of the form that we found in the case of H. Okay, so I'll now state that as a proposition. AZBZ forms a local pair with n as above. If and only if there exist some other quantum fields, Cj of z, such that what's going to happen? Now the commutator AZBW going to be given by a sum 0 to n minus 1 CJW times various derivatives of the delta function. Okay. So in this proposition, one direction is clear. If one has an expansion like in the blue box, then from what we've seen about the delta function, we know that the commutator is annihilated by z minus w to the power of n. So if there's an expansion of this form, then certainly A and B form a local pair. So the tricky part of the proposition is to prove the opposite implication. And I think, so I have notes on this, but I think I might skip the proof because it's kind of difficult to write on this tablet and it'll end up taking a long time. So I'll provide notes somehow to anyone who's interested. But yeah, for the moment, take my word for it. This is an elementary computation. Okay. So let's think about what we have so far. So we have a vector space, quantum fields. We've seen that if there's this notion of locality, we have an example of all of this, which is the oscillator of the algebra acting on the Fock space. And we have the sort of idea that if you have a pair of local fields, then when you look at their commutator, you're able to extract a list of further quantum fields that I've called Cj here. Let me write it in the example. A of z is B of z is H of z. Then what we found is that C0, there is actually no C0 term, but there is a C1 term, right? Because what we found was the first derivative of the delta function. And C1 was really just IH, okay? So this is sort of a trivial example of a quantum field. It's just a constant endomorphism concentrated in 1 degree. So it's very obviously a quantum field. Constant quantum field. So more generally, we imagine an operation that takes A and B and produces this list C0, C1, C2 up to some finite number, okay? And we want to imagine this operation as a kind of product in our vector space V, right? But it's a product that takes as input quantum fields and gives as an output a list of other quantum fields. Now, there's many different ways of kind of organizing this information. So the one that I like is something called a lambda bracket. So what we do is we define A lambda B to be sum of these Cj's. J goes from 0 to n minus 1. And we put lambda to the j over j factorial, okay? And again, this j factorial is, you can think of this as a purely conventional device. Obviously, we didn't have to put j factorial, but it turns out later on the formulas that we're going to derive are nicer when we have this factorial there. So we just put it in from the beginning. So let's write like 1 for the this unit quantum field, and H for H of Z, then this lambda bracket is saying that H lambda H is 0 plus lambda times 1. So let me remark also, arises a proposition, call this part B. Previous was part A. There exists a formula for the CJWs. It is as follows. So I'll explain this notation in a moment. So this formal residue symbol that says, it just says if you have an expression, which is a formal power series in powers of Z, positive and negative, you simply extract the coefficient of Z to the -1, okay? So like in the residue theorem. So we do this with the commutator of AZ with BW, we multiply by Z minus W to the J, and one can show that, CJ now of W is given by this residue, okay? And really part A and part B of this proposition are proved together by a sort of induction on this number N that appears in the locality property, okay? Okay, so that's most of the ingredients of vertex algebra already, but there is one more, and that's the thing we saw right at the beginning, which was this construction of L, of the operators Lm from the operators H, K, right? Let's use this notion of normal ordering. So the normal ordering is the other key ingredient in the notion of vertex algebra. So let me return to that now. Let A of Z, B of Z be quantum fields on a vector space V. Then define A of Z. No, I'm probably going to forget the convention on this. Let me just check. A of Z plus, by definition, is a bit tricky as we define A of Z plus to be that half of the quantum field where the index n is negative. But you see, really, this just means we take the positive powers of Z, okay? And AZ minus is the other part of the quantum field, okay? So A of Z equals A of Z plus A of Z minus. And now the normally ordered product of A and B is by definition the following. We write it with these funny dot symbols. So this is A of z plus b of z plus b of z a of z minus. Okay, so we simply, it's a weird thing to do, but it is what it is. So we take the quantum field a of z, split it in half, positive and negative parts, and we move the negative part to the right. That is, we move the a sub n, where n greater than 0, to the right. Okay. Now, I'll leave it to you to check the following. If we write L of z as sum of Lm, so these operators Lm that we had before, so I'm going to put these into a generating series. And now somehow, because, well, the statement I want to make is that L of z is, remember that we had a half times some normally ordered product of operators h. So it's hz, hz. Okay, so this is what you're supposed to check. And now, because hz had a sum over hm times z to the minus m minus 1, when we multiply two h's together, we're going to get like a minus 2. So for that reason, I'm going to write a minus 2 there. And now the conventions will match up, and you can check that this equation is true. Okay. So I'll state it as again as a proposition. The normally ordered product quantum fields is well defined and again a quantum field. So in particular, this field L of z is a quantum field acting on our Fock space. Okay. Make a remark. That we can unify the definitions of Cj and AB. So you notice now, so as always, the tendency is to try and remove these formal variables from consideration, right? So we defined, for example, A of Z as this formal series, it's a quantum field. We want to start writing A instead of A of Z and thinking of this as a single object, and then talk about these coefficients Cj as being defined as a product of A with B. And similarly, we have the normally ordered product of A with B, which is another quantum field. Now, the definition of AB is, as I wrote above, using A plus and A minus. There's actually a different way to write it. This is not really easier, but you'll see that it's more similar to the definition of the Cj. So A, let's write A, I'm going to write W instead of Z, BW. Residue in Z. Okay, so you see this definition is a little bit complicated. But for any integer n, we can do the following thing. We'll take the expansion of z minus w to the power of n in positive powers of w, multiply that by a of z times b of w, minus, and then do the sort of a similar thing in the opposite order. Take the expansion in positive powers of z times b times a, and then we take the residue in z, so the result depends only on w. And the claim is that this is again a quantum field. If a and b were both quantum fields, then the result is a quantum field. If n is j greater than or equal to 0, this recovers Cj of w, okay? Because in that case, the expansions in positive powers of either w or z are both expansions of a polynomial, so we get the same thing both ways. And then we subtract and we just get a power of z minus w times a commutator. If n is minus 1, we get precisely the normally ordered product. Now you might ask, what happens if we take other negative values of n? Turns out we don't get anything very new. So also a w, let me write minus k minus 1, where I'm thinking of k as being greater than or equal to 0 on bw. Well, this is actually the same as the normally ordered product of the kth derivative of a with b, okay? So we could either think of this set of products indexed by the integers n, or we could think of three separate things. These coefficients Cj, which correspond to the positive products, the normally ordered product, which is n equals minus 1, and the operation of taking the derivative of a quantum field. And it's easy to see that the derivative of a quantum field is also a quantum field. And then those three ingredients, derivative, normally ordered product, and coefficient Cj, are the same thing as taking these nth products for all integers n. Okay, so now let's say definition A. Vertex algebra. There's a vector space V. An element, a vector we call 1. This is called the vacuum vector. A set F of quantum fields on V. And an endomorphism T from V to V called translation operator. Such that so the first axiom says that T annihilates the vacuum vector, and that commutation of T with any quantum field in our set F implements the derivative of that quantum field. Remember, yeah. So it's sort of saying that we need to have an operation of differentiating quantum fields, and for reasons that'll become clear in the next hour, we sort of need this to be implemented by some internal operation in our vector space V. So we have that. It's one of the axioms. The next thing is that V is spanned by vectors A1, N1, A2, N2, up to AS, NS, applied to the vacuum, where A, J are fields in F and the NJ are integers. So this just says we have a collection of quantum fields. Each quantum field has a bunch of coefficients. And if we arbitrarily apply coefficients recursively, then we generate everything in V from the vacuum vector, okay? This axiom is actually not very important because if it were not satisfied, we could just replace V by the subspace spanned by the monomials that I just wrote, and then we would have a vertex algebra satisfying the definition, okay? The really important axiom is the following one, which is that all pairs AZ, BZ in F are mutually local. Okay, so we have one example already. V will be our Fock space H. For the vacuum vector, makes sense that we're just going to take the unit polynomial in H, 1. Now, a set of fields, we're going to, it turns out we only need one quantum field, right? Because by definition of H, it's pretty clear from the definition of H that it is generated by, generated from 1 by the coefficients of this field HZ, okay? So that's the only quantum field we need. And luckily, H of Z is mutually local with itself, so that's good. The missing ingredient is T. T is a little bit tricky. So you can actually, well, one way to say it is that T is going to be specified by the axioms that it's satisfied, right? So already T applied to 1 has to give 0. And this condition here says how the T has to commute with all of the operators Hn. Well, it's pretty easy to see that's going to determine how T behaves on all of H. So you could actually write down an explicit formula for T. It's a little bit complicated. What I'm going to say is the following. T actually ends up coinciding with this coefficient L minus 1 of the quantum field L of Z that we constructed already, okay? So maybe I could say, you know, exercise, check that this satisfies the axioms. Actually, that goes for the whole structure, right? Exercise, check that this quadruple forms a vertex algebra, in fact. So maybe the 5 minutes before noon, I'll say kind of what I want to do in the second hour. So I said at the beginning that the whole point of vertex algebras, or one of the points of vertex algebras, is to be able to sort of do computations like the one that resulted in the Virasoro relations for the coefficients Lm. So we've seen the definition of vertex algebras. We haven't seen yet how they help with this kind of computation. For example, I'd like to compute the commutator bracket of LZ with LW, right? Because then the left-hand side is just double sum on M and N of LM, Ln, Z to the minus M minus 2, W to the minus N minus 2. And then right-hand side is going to equal something, and then equation coefficients. Gives Lm, Ln, right? Kind of that's the point. So well, that's the perfect moment to have like a 5-minute break. So I'll be back in 5 minutes. Okay, so welcome back, everyone. So the next thing I want to say, so I need to develop a little bit of theory of vertex algebras in order to get to a point where we can start doing computations. The theory I want to mention is so-called state field correspondence. Because at the moment, it's a little bit strange that one would call, well, the structure that I've just defined and called a vertex algebra, why would one call this an algebra? Like, what's the product? We've seen there are various operations. There's the operation of taking these CJs, there's the lambda bracket, the normally ordered product. But, you know, an algebra should be a vector space with some product, possibly more than one product, and some axioms saying how the products relate to one another. So state field correspondence puts the notion of vertex algebra more into that sort of form. So to explain it, let me introduce some following notions. So let V, 1, T, and F be a vertex algebra. Let, going to define F tilde to be all quantum fields such that T A Z equals its derivative. Okay, so this is some very large collection of quantum fields. These might not be mutually local with each other by any means. At the other extreme, we have F itself. And this is inside F tilde by definition of a vertex algebra. Okay. And in between, we're going to consider F bar, which is let's say all iterated nth products of AI of Z in F. Okay. So this just means it's all the quantum fields from F, nth products of such fields. So as we've seen already, these are, again, quantum fields. So we get further quantum fields. And then we take nth product between these new quantum fields and the original quantum fields, and we just keep doing this again and again and again to infinity, okay? So F bar is a sort of envelope of F in some sense. And I'm also going to do the following thing, F prime, which is going to be the set of B, so the sort of translation invariant quantum fields with the property that B of Z is local with all the fields in F, okay? So you think of this as a sort of commutant in a sense, right? So we have a bunch of fields F, and then we take some field which is local with all of those. Okay, so in particular, since F consists of mutually local fields, F should sit inside F prime. Actually, we now have a lemma. This is called Dong's lemma, which says if A, B, C mutually local, then AN and B is local with C for all N in Z, okay? So this is a simple calculation to prove this lemma. It's a little bit well, yeah, it's slightly complicated, but it's an elementary computation. But it's a very important fact. So if we have three mutually local fields, then the nth product of any pair of them is local with the other. So it's pretty easy to see that this implies that, so we had our original set of fields. Then we formed this sort of envelope, completing it. And luckily, all of these fields in this envelope are local with the original fields in F and with each other. So that means that they all sit inside this sort of commutant set of fields. And that in turn is inside F tilde, the set of all translation invariant fields. Okay. Now, theorem, I'll say part one, if A of Z is any field in this big set, then there exists a vector V such that when we apply our vector to the vacuum, we get, I'm going to write e to the Z t v. So that looks a bit scary, but I just mean the series expansion of this exponential, v plus a half Z times tv plus 6 Z, oh, I'm sorry, not a half, ZTV plus a half Z squared T squared V plus so forth. So we define S from this big set F twiddle to V, which just sends a field to this element V. So this V is unique also. All right, so we have this linear map S. Part two is that this S behaves very nicely with respect to the nth products of the fields. So if we take an nth product and apply S to it, what we get actually is S of B of Z. So recall this is an element in V, and we get A, its nth coefficient applied to that vector, okay? And now recall at the beginning I said that our choice of convention for putting the coefficients into a generating series was more or less arbitrary, but it was sort of a convenient choice of convention. Well, this is sort of the point at which we see it's particularly nice to choose to index our coefficients in this way so that it gets along well with this other notion of nth product between quantum fields. Okay, so there's a kind of, so we have S, which is sort of intertwining a set of fields and the underlying vector space in a certain sense, right? It's sending, yeah. So the third part, and this actually is I'm writing as one part of a theorem, but it's actually an independent theorem on its own. So I should write the name of the guy. This is due to Goddard. And the statement is, if we take a set G of translation invariant quantum fields with the property that S of G covers all of V, okay? So the restriction of S to G is surjective. And if A of Z is local with all B of Z and G, it's a little bit complicated, the statement, but we'll see why it's relevant in a moment. If S sends this field A to 0, then in fact A had to be 0 already. So this is a kind of injectivity statement for S, all right? So now I'm a bit in doubt as to how many of these statements to prove. Let me prove the first one anyway. So recall the first one was that if we take translation invariant field and apply it to the vacuum, then we get something with only positive powers of Z. And so if we take the 0th coefficient and call it V, that's a well-defined element in underlying vector space V. Okay, so how do we get this? Well, let's write A of Z applied to the vacuum as little V of Z, and call this a sum of V sub n Z to the n, right? So the Vn's here are elements of V. Now, since the commutator of T with AZ implements differentiation, and T by definition annihilates the vacuum vector, we find actually that Vn equals 1 over n TV n minus 1 whenever n is different than 0. But we also know AZ is a quantum field. So Vn is 0 for all n, let's say, very negative, okay? So when n is sufficiently negative, we have Vn equals 0. But then we just recursively apply this relation here to deduce that, if some very negative Vn is 0, well, then the next Vn 1 up from there is also 0. And this goes on all the way up to n equals minus 1. All V subscript less than 0 are equal to 0. So our A of Z vacuum is actually in the power series in Z. So write V for this guy, AZ vacuum, and then set Z equals 0. That's well defined. And now this relation, which I've now called star, again implies, well, it tells us what V1, V2, etc. are. So we actually get this result. Okay, so the S is well defined. Maybe I'll prove the second part as well. And then I'll leave the third part. So the second part is we'll consider I'm going to use W in BW applied to the vacuum vector, right? So this is going to give us our S, right? So recall the statement was that if you apply S to an nth product of quantum fields, then you get one of the coefficients of the first field applied to S of the other field. Okay, so we'll apply this guy to 1. Now we'll open up the definition. Oops. So this is residue in Z now of AZBW applied to 1. There's an expansion Z minus W minus BWAZ supplied to 1 WZ to the N. And now I claim that the second term vanishes completely. Why is that? Because this series here has positive powers of Z, right? By definition. This term here also has positive powers of Z, as we've just seen in the first part. So when we take the residue, which is to extract the Z to the minus 1 coefficient, this entire second term is going to vanish. What we get is residue in Z, AZ, and actually this BW applied to 1 is e to the WT S of BW, multiplied by Z minus W to the N. Okay, now S was supposed to be given by, so remember we wanted S of AW in BW. So that is given by taking the expression above and setting W equal to 0, right? But if we set W equal to 0, then we get, okay, sorry, yeah, so this is not quite true because I still haven't set W equal to 0. So here I'll e to the, oh no, it was right, yeah, S of BW. Okay, now we set W equal to 0 and we get residue AZ S of BW Z to the N, which if you stare at it for a while, you'll see that is just the nth coefficient of A applied to our S of BW as required. And then 3, I'll leave, well, as an exercise, or as I say, I have notes, or, you know, in standard textbooks also, you can find the proof of this part, this Goddard's theorem. So this is, recall what Goddard's theorem says. It's if you have a set G of translation invariant quantum fields, and it has the property that S of it is surjective to V, then if you have something that's local with everything in G, S is injective on that field then. If S annihilates that field, then actually the field was 0. So let's take a corollary, these 3 parts. So the first is that the restriction to this completed set of fields is surjective. The second part is that the restriction to this commutant set of fields is injective. Okay, and how's the proof of this? So the proof of 1 is pretty clear. It's that using the previous part, using the theorem, you know that S behaves well with respect to nth products, right? So say it this way: A1 of Z, N1, A2 of Z, N2, etc. AS of Z, NS. 1 actually is just A1, N1, A2, N2, so on. AS, NS. And this sort of completeness axiom of a vertex algebra now comes into play. It says that these vectors precisely span V, okay? So we've just shown that S is surjective and restricted there. Now, S restricted to the commutant is injective. This comes from the Goddard theorem item, so part 3. And again, I'll leave it to you to think about, but it's pretty clear at this point how to apply that part of the theorem to this situation. Okay, and I'll continue with the statement of the theorem. So part 3 says then S restricted to this F bar is a linear isomorphism. Now, why is this true? Well, we've just seen that, so go back. So we have F bar inside F prime, and we've seen that the restriction of S to F bar is surjective, but F prime is bigger than F bar. But we've also seen that the restriction of S to F prime is injective. So actually, F prime and F bar have to be equal to each other, and the restriction of S to both has to be an isomorphism. We've established an isomorphism between V and the set F bar, the sort of completed set or envelope of quantum fields. So let's denote by Y the inverse of S, that is for A in V, we get Y of AZ, a quantum field acting on V. Then if you take the quantum field associated with A, take its nth coefficient and let that act on B, and then take the quantum field associated with that, you'll find that it equals the nth product of the quantum fields associated with A and B. And this again is basically clear. If you think about it for a little while, you'll see that it's just a restatement of this second part of the previous theorem that says that S gets along well with nth products and coefficients of quantum fields. Okay. So now we have the notion of vertex algebra in a form that looks a lot more like an algebra, right? It's a vector space V, and it has a bunch of operations which take a pair of vectors and turn them into new vectors. And these operations satisfy some kind of identity, which is summed up by this equation here. So this equation, if you could now expand it out, call it star again, could expand star in powers of Z and obtain an identity that involves A and B and all the various nth products for different values of n, which is called the Borcherd's identity. Okay, so I don't want to write out the Borcherd's identity explicitly, but I hope you can appreciate that there is a way to kind of undo everything we've done and sort of write out the definition of a vertex algebra without mentioning quantum fields at all in some sense. Then you get some kind of weird algebraic structure whose definition is kind of quite difficult to understand intuitively. But somehow we got to it from this very natural sequence of operations involving quantum fields and normal ordering and expansions and so forth. Okay, so I'll jump ahead a little bit and say how to express this Borcherd's identity, or rather how to express, how to express the Borcherd's identity in terms of the lambda brackets and normal ordering, so that finally we can start doing some computations. Okay. Just a remark. What I've been calling the lambda bracket is actually more commonly called the OPE, or operator product expansion of A and B. So you'll often see in the literature this expression OPE. Okay, so we have some identities, which I'll write out without proving. For example, if I take a derivative of A, actually I should use T. T A lambda B is minus lambda A lambda B. A lambda, if I differentiate the second term, I get T plus lambda applied to A lambda B. We also have, if I take T of a normally ordered product, this is normally ordered product of TAB plus ATB. So T is a derivation of the nth product. There are also some more complicated ones. One of them, this is often called skew symmetry, and you'll see why, is that lambda bracket of B and A is given by minus A minus lambda minus TB. Okay. So this kind of probably needs a little bit of explanation in terms of interpretation. So what this is if A lambda B is a sum of Cj, I'll write it this way, lambda j over j factorial Cj, then when I write minus lambda minus T, B, by definition, I mean sum of minus lambda minus T, j over j factorial Cj. And you see, when you expand out this expression here to the power of j, you use the binomial theorem. There's no problem in doing that because j runs over non-negative integers. And then each power of t, you apply it to Cj, okay? So you'll get some sort of polynomial expression that way. So that's what that means. Okay, the most interesting one is, this is something called the Wick formula, which says that a lambda bracket between A and a normally ordered product is given by normally ordered product of A lambda onto B plus similar thing, but B here, and now A applies to C, plus something that looks a bit weird, an integral. Basically what happens is we get a lambda bracket of A with B, which is then applied to C, this new variable mu, and then we integrate. And again, this integration is completely formal. The expression inside the integral is a polynomial in lambda and mu, whose coefficients are elements in our vertex algebra V. Every time you see a mu, every time you see a mu to the power of k, you just replace it with lambda to the power of k plus 1 over k plus 1. That's all the integral means. It's a completely formal operation. Okay. I won't explain how because there's no time, but all of these identities can be derived from the Borcherd's identity. Some of them, particularly these first couple of identities, don't need the full force of the Borcherd's identity. You could have derived them already before I even gave the definition of a vertex algebra. But the last of these identities, the Wick formula, this really is only true when we have the full kind of power, if you will, of the vertex algebra axioms. Okay, so now, finally, as promised, I want to do some computations. So we had our vertex algebra H. By the way, H stands for Heisenberg, right? And this had one generating field H, which was given by a lambda bracket HH is lambda times the unit field. And often I'll just omit 1 from computations, right? We had L, by definition, 1/2 the normally ordered product of H with itself. And now we want to compute L lambda L. Well, first let's compute H, well, L lambda H. H lambda L, that's a half H lambda H, right? So you would then use the Wick formula to simplify this expression. And you get this integral and everything. In this case, the integral actually vanishes because we'd be taking the lambda bracket of 1 with something. So, by the way, 1 lambda v is 0 for all v. Okay, so you do that computation, then, so it is what it is. I won't work it out explicitly, but you'll find you then use skew symmetry to work out L lambda h, and you find that it equals th plus lambda h. Okay, so this is something that you can compute. And then if you wanted, you could expand this, and you discover that, like, for example, L0 commutator hm is, oh, what's it going to be? I think it's minus mhm, for example. So I'll leave that as an exercise, firstly, to do the lambda bracket computation, and then also to interpret these things as quantum fields, extract the appropriate coefficient, and deduce this commutator bracket. Okay, but now I want to continue. So now L lambda L is going to be given by a half L lambda normally ordered product H with H again, right? So we're using again the definition of L. And we again use the Wick formula and compute. The computation is much more interesting this time, and this time a non-trivial integral will appear. Again, I'll leave it as an exercise to do the computation. What you'll discover is that one gets TL plus 2 times lambda L plus lambda cubed over 12 times our unit field. Okay. And this 12, I mean, I guess it's as mysterious as it ever was, but somehow it appears in this case, from this integral, somehow a lambda multiplied by a mu squared appeared, and there was also a half coming from the definition of L, and then integrating the mu squared gave a 1 over 3, and somehow eventually this 1 over 12 appeared. So what this says, or more accurately, what this means by definition, is that LZ LW equals the W derivative of LW times a delta function plus 2 times LW times the derivative of the delta function plus a 12th times the third derivative of the delta function acting on H. Okay. And as commented before, oops, typically one would put C here and say, just in this case, C is equal to 1. This is the central charge. Exercise. If I set B to be L plus, what do I want to call it? Beta times TH, okay? Where now beta is just some scalar. You can do this computation again explicitly, and it's a good exercise for anyone who wants to get better at this kind of computation. So this is again a Virasoro field. One finds is lambda cubed over 12 times 1 minus 12 beta squared. So this is a Virasoro field, central charge C 1 minus 12 beta squared. So you can actually construct representations of the Virasoro algebra at all kinds of different central charges just by varying this field. This kind of computation would be very painful to do if you didn't have this vertex algebra language to organize the calculations. Okay, so I guess the last thing I'd like to talk about are some other examples of vertex algebras. So let G be a finite dimensional Lie algebra. And GG, so this here is a invariant bilinear form on G. So from these we have the corresponding affine Lie algebra, which is almost a Kac-Moody algebra, given by G hat as G polynomials, Laurent polynomials, CK, AT to the M, BT to the N, ABT M plus N plus delta M minus N, M, ABK, K is central. And we have highest weight representations for this Lie algebra. Like U of G. I guess what you tend to do is say N plus hat. This is the oh, I guess I should call it B plus Borel. So this is the finite Borel plus EGT. Okay. Actually, I just realized implicitly, so I made a point of, sorry, the M here, A. So I had made a point of saying you could do this construction for G, any finite dimensional Lie algebra with an invariant bilinear form. It doesn't have to be simple Lie algebra necessarily, though if G is simple, one has a natural choice, which is the killing form, which is non-degenerate. So actually, by far the most important case is to take G to be simple or semi-simple. But then already when I start talking about representations, implicitly I assume that G is simple so that I start talking about a Borel. But anyway, there's that construction, but there's a particular class of these highest weight modules where you don't even need the choice of Borel. You can highest weight. So these are Verma. Sorry, and I called them L. I meant to say M. So this is the Verma module. So one, there's Vermas. Two, something called a vacuum module. So this is quite similar to a Verma module, but what it is V is U of G hat tensored over U of G hat plus C, maybe I'll call it 1 suggestively. And here G plus is our central term plus G polynomials in G. And we'll say that A t to the m acting on 1 is 0 for all m greater than or equal to 0. K on 1 acts by some parameter k called the level, and I'll call this VKG, like that. Okay, so what does this gadget kind of look like? You could think of it as having this kind of triangular shape. There's 1. Here's a copy of G, right, where you identify a vector A t to the minus 1 with the corresponding element A in G. And then further down, you get other elements like A t to the minus 2 or A t to the minus 1 times B t to the minus 1, etc. Okay, so this is a picture of VKG. The claim is that this is a vertex algebra in a natural way. So to be a vertex algebra, VKG is our vector space. 1 is the vector that I've been calling 1. T I'll come back to in a moment. What about the fields? Now, instead of just one generating field, there's going to be a bunch of them. There's going to be one generating field for every one of, let's take a basis for G. So I'll call these A of Z, where A are elements in G. So explicitly, I have to say what A of Z is. So this is the sum of n runs over the integers, and the nth coefficient, A sub n, is going to be the operator A t to the n, okay? So this acting in our representation Vk of G, okay? So we have one of these quantum fields, well, yeah, so we have one of these power series for each element in G. Claim, they're all quantum fields. This is kind of clear from the construction of the underlying vector space V. It's very similar to the Fock space representation of the oscillator algebra. Then so the AZ are quantum fields. Now, if we compute a commutator of 2 of them, this is a good exercise to do. You'll find that the commutator ends up being the field associated to the commutator of A and B multiplied by the delta function plus a derivative of the delta function times K, which is now acting by the identity in our space. So this is an explicit computation that you can do. So expressing this in the lambda bracket language, you find that A lambda B is the field associated with the bracket of A and B plus a lambda term, AB, K. Okay. So in particular, these fields are all mutually local. And I said I'll come back to T. So T is, again, a little bit complicated to explain what it is, but just trust me that there is a T, and together with the data I've just described, this is a vertex algebra. So there's something we can do called the Sugawara construction. And this says, so this we do as follows. So it's again going to be a construction of a Virasoro field, this time acting in our affine vertex algebra, VKG. So actually now let G be simple. And this guy non-degenerate. So it's a multiple of the killing form. Let x1 through to xn be a basis. We'll take the dual basis given by xi, yj, delta ij. So something appeared in the chat. Oh, yeah. Okay. And so I'm nearly finished. We have a pair of dual bases, and now we'll define L to be normally ordered product of the field xi with the field yi, 1 to n. And we have to normalize this. So in the remember in the case of the oscillator algebra, we had something similar, like 1/2 times h with h. Here we're taking a sum of xi's, and we have to normalize by something a bit more peculiar, 1 k plus h check. Okay, we're here h check. It's the Joule-Coxeter number of G. Then it's a proposition that L of Z is a Virasoro field on VKG of central charge actually I can't remember the formula. I think it's 1 over k plus h. H check times the dimension of G. Something like this. So this construction, so we have a representation of Virasoro in our VKG. And let me just conclude by saying this has important applications in constructing unitary representations of the Virasoro algebra. Okay, so you could view all of this as kind of the Virasoro algebra being this very important Lie algebra that appears in physical applications, because as you probably know, the Virasoro algebra is the unique central extension of the Witt algebra, which is the Lie algebra of vector fields on a punctured disk. So that's an important Lie algebra. I mean, it's simply an important Lie algebra. So Virasoro is important. Constructing unitary representations of Virasoro was quite a difficult task in some sense. And so you need some way to sort of get your hands on interesting representations of this Lie algebra. And so we saw at the beginning of the talk that there was this method of starting with the oscillator algebra acting on the Fock space, writing down these peculiar infinite sums, which were then able to show satisfied the relations of the Virasoro algebra. And Vertex algebra sort of arise as a way to organize that kind of computation and make it a bit easier. And finally, one discovers that there's a broad class of vertex algebras which are constructed from finite dimensional simple Lie algebras. And again, there's now a more sophisticated way of constructing Virasoro representations there. And in this way, you can get your hands on all the irreducible unitary highest weight representations of Virasoro. Again, because the Vit algebra is vector fields on a formal punctured disk, it has relevance to complex geometry, to the theory of Riemann surfaces. And indeed, kind of this construction of representations of Virasoro inside vertex algebra is also very important in geometry of Riemann surfaces. So anyway, time is up, so I'll stop there. And yeah, I mean, I'm happy to continue like answering questions if anyone has any questions. So